Have you ever just hit a wall in math? You know, a problem that seems completely impossible? Well, for centuries, that's exactly where mathematicians were stuck, until they did something brilliant. They invented a whole new kind of number. Today, we're diving into a crash course on complex numbers, and I promise, by the time we're done here, they won't feel so complex at all. So yeah, let's get right into it. We all start out with this, right? The good old number line. It's super simple, it's one-dimensional, you can go right for positive, you can go left for negative. It's perfect for things like adding and subtracting, which is really just sliding back and forth. But this simple line, it has a hidden limit, a question it just can't answer. And this is the showstopper. What number, when you multiply it by itself, gives you -1? I mean, think about it. A positive times a positive is positive. And a negative times a negative, well, that's also positive. So our number line basically tells us that the square root of -1 is impossible. It's a dead end. Or is it?
To crack this, we have to rethink what multiplication is actually doing. Let's say you take a number, like +3, and you multiply it by -1. You get -3. On the number line, you've just done a complete 180-degree flip across the center, the origin. Multiply by -1 again, and you flip 180 degrees right back to where you started. So 2 180-degree flips bring you full circle. And this is the light bulb moment. If multiplying by -1 is a 180-degree turn, what would a 90-degree turn look like? What could we do twice to get that full 180-degree flip? Answering that one question changes everything.
And here's the answer. We call it I, the imaginary unit. By definition, I is the square root of -1. Now, listen, the name imaginary is kind of terrible. It was a historical accident. It's not imaginary like a dragon. A much better way to think about I is as a new direction, a 90-degree turn away from the number line we're used to.
So if you think about positive and negative numbers as moving left and right, or east and west, then imaginary numbers are just the directions for moving up and down, north and south. See? We haven't invented some fantasy number. We've just added a second dimension to our world. We've gone from a line to a whole plane. And this cycle is just beautiful. It shows you the rotational power of I so clearly. Multiplying by I is always a 90-degree turn counterclockwise. Let's start at 1. Multiply by I, you make 190-degree turn and land on I. Do it again, you're at I squared, which we now know is -1. That's a 180-degree turn from the start. A third time gets you to -I, and one last multiplication by I gets you right back to 1. It's a perfect 4-step rotation. All right, so now that we've got these two dimensions, a real axis for our left and right and an imaginary axis for our up and down, we can start mapping out any point we want. This is what we call the complex plane. So this is our new map, the complex plane, or sometimes you'll hear it called an Argand diagram. That horizontal line is just our old friend, the real number line. And the new vertical line, that's our imaginary number line. Now, every single point on this flat surface can be giving its own unique number. You'll see a complex number written as a+bi, and it's not some weird abstract concept, it's just an address, it's a set of coordinates. To find the number 3 + 2i, you just go 3 units to the right on the real axis, and then 2 units up on the imaginary axis. That's it. Every complex number has its own spot right here on this plane. Okay, so we can plot them. But how do we measure the size of one of these numbers? With a real number, you just ask how far it is from 0. But for a complex number, it's a bit different. For that, we need to find something called its modulus. The modulus is really just a fancy word for the straight line distance from the very center of the map, the origin, out to our number. And if you take a look at that formula, it might look a little familiar. It's the square root of the real part squared plus the imaginary part squared. Ring any bells from geometry class? It absolutely should, because look, when you draw a line from the origin out to your point, and then another line straight down to the real axis, you've made a perfect right-angled triangle. The lengths of the sides are a and b, and the modulus, which we can call r, well, it's just the hypotenuse. So finding the size of a complex number is really just the Pythagorean theorem in disguise. Okay, let's walk through a perfect example. 3 + 4i. Here, our a is 3, our b is 4. So first step, we square them. 3 squared is 9, 4 squared is 16. Got it. Next, add them together. 9 + 16 gives us 25. And the final step, just take the square root of that.
The square root of 25 is 5. So the modulus of 3 plus 4i is exactly 5. Simple, right? So why do we care so much about this distance? Well, this is where it stops being a math game and gets real. In the incredibly strange world of quantum mechanics, a particle's state can be described by a complex number. And if you take the modulus of that number and square it, you get the actual probability of finding that particle in a specific place. Let that sink in. This imaginary math is what we use to predict real, physical probabilities.
Okay, so we've got coordinates, we've got rotations. Now there is one truly remarkable formula that just ties all of this together in the most elegant way imaginable.
The great physicist Richard Feynman, he didn't pull any punches. He called it our joule and the most remarkable formula in mathematics. That's some serious hype. Let's see what he was talking about. This is it. Euler's formula. Now, it might look a little intense at first, but let's just break it down. It says that e, which is a special number like pi, raised to an imaginary power is directly connected to cosine and sine. Those are the functions that describe circles and waves. This one equation is the ultimate bridge. It connects algebra, geometry, and trigonometry all in one place. So why is this a game changer? Well, first, it's the mathematical proof that complex numbers are fundamentally about rotation and waves. And second, it gives engineers this incredibly powerful shortcut. Instead of dealing with A and B coordinates, they can just use a distance and an angle. This makes calculating things like electrical signals or radio waves so much easier. So at this point, you might be thinking, okay, that's clever math, but so what? Let's pull this out of the world of pure numbers and see where it actually shows up. Take a look at this helix, this beautiful spiral. This is what a complex number looks like when it's moving through time. This shape is, quite literally, the mathematical language of waves. And that's the big takeaway. These numbers with the silly imaginary name are absolutely critical for describing things that are very, very real. The signal your phone is getting right now, the electricity powering your screen, the very nature of atoms, all of it is understood and engineered using the language of complex numbers. They are the invisible engine of modern science and technology. Which leaves us with a pretty cool thought to end on. For hundreds of years, the square root of -1 seemed like a useless, impossible little puzzle. And then it turned out to be the key to describing the universe. It really makes you wonder, doesn't it? What other impossible ideas are just sitting around in math right now, waiting for us to figure out how they connect to reality?